was invited to come up here to speak about Mark I, I began to wonder from which point of view you talked about Mark I. And I realized that the environment of the time, most people did not remember. I've perhaps been acutely aware of it because, of course, this is my identifier. And as you all well know, I hope, every record in a computer must have an identifier. That's so you know where to put it and how to get it again. On the other hand, I find that a large number of people no longer recognize my identifier. In fact, I go wandering around airports and people come up to me and say, "When's the next plane leave for Houston?" It doesn't help any. I got totally demoted one night in San Francisco. I got off an elevator, and as I got off, there was a couple in the elevator with me, and I heard the woman say to her husband, "What was that?" And he said, "That was a security guard." So then I had to speak at the University of Guelph in Canada. I had to go through immigration at the Toronto airport. So I handed my passport to the immigration officer, and he looked at it and looked at me and said, "What are you?" And I said, "United States Navy." He took a second real hard look at me, and then he said, "You must be the oldest one they've got." Since I didn't feel that was a polite way to welcome visitors to Canada, all I could think to say was, "No, Admiral Rickover is 6 years older." I don't think he even knew who Admiral Rickover was. And of course, now that Admiral Rickover is retired, I've become the oldest Navy officer on active duty, a somewhat questionable honor. Well, I realized that if people didn't even recognize the insignia on my cap, now I can take my cap off. There were many other things I didn't remember. For instance, when I get interviewed at various times, somebody always looks at me and said, "What made you join the Navy?" I quietly try to say there was a war on. I think we've totally forgotten the environment in which Mark I appeared and what a difference it made in the reaction to her and the problems she ran. 41 was Pearl Harbor. By 43, we were in the thick of things. Very few people here will remember the fact that we looked out off the coast of New England and watched ships go down at sea, torpedo to fire, that the world was in a very, very critical state. Most people have forgotten that everybody in the country tried to do something for that war effort, probably the last time we all worked together. My mother was on the ration board. My father, who'd lost his legs, was on the draft board. My brother was in the Army Air Corps. His wife was at the Office of Scientific, Office of Scientific Development, OSD, I guess it was. She was working there because her husband getting $50 a month didn't do much to support her. My sister was running the nursery school at the big GE plant in Bloomfield, New Jersey. She couldn't enlist because she had 3 small children, so she ran the nursery so that all the women could come to work. In fact, more than once I find people looking at me and saying, "Well, wasn't it unusual for a woman to be doing things like that?" And I have to say, "Didn't you ever hear of Rosie the Riveter?" And I find nowadays there's a whole generation that doesn't know that Rosie the Riveter built the darn ships, the LSTs and all those. That they've totally forgotten what everybody was doing in those years. It was a total effort. I had long wanted to join the Navy as well, but I was in a classified occupation. I was a college professor teaching mathematics. At that time, the teaching of mathematics was a classified occupation. The only way you could get out of it was to get permission. If you couldn't get permission, the only other way you could do is by quitting and staying out of work for 6 months, and then you could join the Navy after all. However, I finally got permission to leave Vassar, and then I faced a second obstacle. I was underweight. For some unknown reason to this very day, the Navy considers that I should weigh 140 pounds. And all these years I've been trying to explain to the Navy that I had Scots ancestry and I'm lean and tough and I don't need to weigh 140 pounds. I weighed 105 pounds, which meant I had to get a waiver on my weight and be permitted. I carded that waiver all the way through the early part of my career, which permitted me to be below the weight tables. That was a great help. However, I was finally accepted and sworn in December of '43. The next thing that happened to us all was they turned us into Navy officers. For most of the men, it was a 90 days of study and learning. And we called them 90-day wonders. They became reserve officers. They're the ones that manned the fleets. In our case, they didn't think we needed quite that much time, so we were 60-day wonders. We spent 30 days as apprentice seamen, the lowest of the low in the Navy, and we learned to take orders. I went to midshipman school at Northampton. I can remember people being dumped out of the Navy because they could not learn to take orders. They were invited out. I had to make it through Northampton because I was overage for enlisted, so that if I didn't make it through to a commission, I'd be out of the Navy. I was 37 years old. The second month, we became midshipmen, and we were in charge of the seamen. And then we had to learn to give orders. And I watched one girl thrown out of the Navy because she screamed at somebody. And you were supposed to give orders in a level voice, clearly, and not yell at people. So we learned for 1 month to take orders, and for a second month to give orders. And then we received our orders. My orders sent me to the Bureau of Ships Computation Project at Harvard. So frantically, this was on a Friday, and I was supposed to report on Monday morning. So I had Saturday and Sunday off with my family, and then I came to Boston. And then I started to find the Bureau of Computation Project. Well, I finally found the Office of Naval Research. They'd heard of it, but they weren't quite sure where it was. So finally, about 2 o'clock in the afternoon, I found the Bureau of Ships Computation Project in the basement of Cruft Laboratory at Harvard. I walked in the door, and Commander Aiken looked up at me and said, "Where the hell have you been?" Well, heck, I'd just gotten out of midshipman school. They'd said I could have the 2 days off, and I'd spent the whole day trying to find the place, so I tried to explain that, and he said, "I mean for the last 2 months." I said, "I was at midshipman school." He said, "I told him you didn't need that. You've got to get to work." He then waved his hand at Mark I, all 51 feet of her, and he said, "That's a computing engine." Now that's a concept we've forgotten. A computing engine. Not a computer, not a calculator, a computing engine. And there's a difference in that point of view, and I think it was in his mind as well. Computers are what we have nowadays. Black boxes, things on chips. One unit, one thing. Calculators, they were those lovely things that sat on your desk and you entered a number and then you ground it out. Well, you multiplied it and then moved it over and you ground it some more. Ground it some more. We did have some electrical ones, but most of them were hand cranked. Certainly Mark I wasn't really a calculator. I think when he called it a computing engine, what he meant was it was made up of different parts that performed different functions. And I think that's a concept we've lost, which we're going to have to bring back again, because we're going to be starting to build systems of computers, some of which will have specialized functions like the new database machines. And I think we'll go to a structure and an architecture was far more like UNIVAC Mark I than we might ever have thought it would be. I think he was right when he called it a computing engine. It really was an engine. It had many parts which worked simultaneously together with each other and performed functions. And it took in numbers and it chewed them up like the dickens and spit out numbers again. And it was a computing engine. Well, having taken one look at me and said that was a computing engine, he informed me that he would be delighted to have the interpolation coefficients for the arc tangent by next Thursday. Well, by this time, I'd have been introduced to the two programmers who were ahead of me. Ensign Robert D.V. Campbell, V.D. Campbell, and Ensign Richard M. Block. Shortly after I met them, I found that they'd been very thoughtful in preparing for me. They'd heard that this white-haired old school teacher was coming, so they'd tried to bribe each other as to who should sit next to her. However, they were most kind to me, and they did help me get my first program onto the computer and compute the coefficients of the arctangent interpolation function. It was a very small crew. There were very, very few of us when we started. There was Commander Aiken and Ensigns Block and Campbell. There were 4 enlisted men who operated the computer. They were called Specialist I, and their insignia was a diamond with an I in it, and the I, of course, stood for IBM. Dello Calvin, Hugh Livingston, John Mahoney, and Durwood White were the original Specialist I that started with us. Later, we were joined by Frank Verdonk, who was the yeoman. And as normal and usual in the Navy, it was the yeoman who brought order out of chaos. He even disciplined the commander at intervals. Another officer joined us, Lieutenant Arnold, and still later, Ensign Lockhart and Ensign Brendel. We also had civilian members of the crew, of the Harvard staff. Later, there was a chief and a motor machinist mate. But it was a small group, and small, tight group, and a very big machine, because Mark I was 51 feet long, 8 feet high, and 8 feet deep, and she was in a magnificent glass case eventually, designed by Norman Bulgettis, which of course made it better than ever. Perhaps if you looked at it today, I think no one looking at it today would really believe it was a computer. You'd hardly believe it was a calculator when calculators come this big, and that thing was 51 feet. It would be hard to recognize Mark I in today's world. Yet if you go back to that time and to the need for computation, she begins to take her place in history. In the first place, she was the first large-scale digital computer in the United States. The first machine that was built that was supposed to assist the power of man's brain instead of the strength of his arm. From that point of view, she'll always be recognized. Even though many more computers were built during the war and later, Mark I will always stand in that position of first. There's something else we've forgotten about her. She was automatically sequenced. She was programmed, step-by-step program exactly as we have today. Everybody talks about ENIAC because it was the first electronic computer. But ENIAC was not programmed. He used patch cords and put that together in a simulation of the problem you wanted to solve. It was not programmed when it was built. That was added somewhat later. So that from that point of view, Mark I more closely resembled what we have today than any of those other early machines because it was sequentially programmed, step by step, one operation after another. Of course, it had one characteristic which today's sequenced program computers don't have. If you didn't tell Mark I to go ahead and do the next operation, it stopped. You had to put that 7 on there, or else if she didn't get that signal, or another automatic signal, she just stopped dead and waited for you to tell it what to do. From some points of view, that has a tremendous advantage. It was wonderful for debugging. But I think she was the only machine that was ever built that it stopped at the end of every single operation. And, unless you had that 7 or another automatic in there. There were a lot of adventures with Mark I, some of which have become slightly historical. At the same time we were running Mark I, we were starting to build Mark II for the Navy. And Mark II was built entirely out of relays in an awful rush because the war was on. And we were building Mark II the summer of 1945. And naturally, since it was World War II, we were working in a World War I temporary building. The air conditioning wasn't very good, the screens weren't very good, and the windows were all open. Mark II stopped. They finally found the failing relay. And inside the failing relay, bitten to death by the relay contacts, was a moth about this big. So the operator got a pair of tweezers and very carefully fished the moth out of the relay, put it in the logbook, put Scotch tape over it, and below it he wrote, "First actual bug found." Of course, when Commander Aiken poked his head in the door and said, "Are you making any numbers?" If we weren't making any numbers, we told him that we were debugging the computer. Of course, I've told that story a lot of times. Turned out some people didn't believe me, among them AFIPs. I had also explained that the bug is still in the logbook under the Scotch tape, and it's in the museum at the Naval Surface Weapons Center at Dahlgren, Virginia. So AFIPs decided to check up on me. They went down to Dahlgren, and sure enough, they found the first actual bug in the logbook. So they took a picture of it, and they published it in the July 1981 issue of the Annals of the History of Computing. So the first bug is now legal. Something else happened as a result of that. There was an area in Boston known as Scully Square. It was off limits to waves, you understand. And at the corner, one of the corner stores in Scully Square, there was a magic store. And somebody was down there one day and discovered in the lower front window of the magic store a box of fake bed bugs. Nobody ever knew quite how it happened, but about 2 or 3 days later, it turned out that Mark I was full of bed bugs. Commander Aiken ordered up all of the vacuum cleaning equipment in Harvard University and vacuumed Mark I. Well, that took all the dust out of the relays, so they didn't make contact anymore. And so she didn't run for another few days either, because they'd cleaned her up. There were many very interesting and historical developments. One of the reasons we so greatly needed computation is another thing most people have forgotten. World War II saw an almost complete change in our weapon systems. Up to that time, when you had a mine, the mine had ears sticking out of it. And the ship had to hit the ears and break a connection before the mine went off. All of a sudden, we started building acoustic mines that listened for ships, magnetic mines that waited for to sense the metal of the ships. Well, now we had to know how big was the effect of the mine. How much area was it going to detect ships? So all the computations had to be created to tell us how much space around a mine would this mine affect, so that we know how close to sow the mines, where to position them. The same thing happened, of course, with the acoustic mines and the magnetic mines. Up to that time, for depth charges, we'd roll those things that looked like big oil drums, roll them off the stern of a destroyer. All of a sudden, they were propelled by rockets. The question was, where would they go, and what pattern would you fire? We began firing out of guns, missiles, or instead of lobbing just shells, the darn things were self-propelled. They had rockets in them. How far would they go? We put proximity fuses on them. You no longer had to hit something directly. You had to hit in its area where the fuse could detect it and go off. All new weapons. Most people don't realize that the Navy even had a couple of guided missiles, the Bat and the Grebe. The Bat was one of the funniest things you ever saw. It was a 600-pound bomb with its usual round tail with fins and a wing put across the top of it. And a pilot dropped one from his plane and by radio, he could control the direction of slightly control the direction of the bomb to make a better hit. All of this required new computation, tremendous computations. Even after you'd found out where the mines would detect a ship and go off, then you had to know what kind of a dipole you'd tow behind a ship in order to sweep the mines when you wanted to get them up out of the way later. And what was the influence of the dipole and how much strength would it take to detonate the mine. So there was a tremendous amount of computation to be done, including the A-bomb and all the other things that happened during World War II. And the pressure for that computation was very great. Everything was hurry up, do it yesterday. So the pressure to keep the only computers we had running was very, very strong. And Mark I ran 24 hours a day, 7 days a week, which was a very rough task for a small crew. Mark I had several parts, as I've mentioned, several units. One thing was taken over from the verbiage of Babbage. Babbage's computer had a store and a mill. And the store was where you put the numbers. And the mill was the thing that worked on the numbers, essentially what we would call today the sequence mechanism. We've since used that word, has come to mean storage, and we talk about it all the time, but that has a long descent all the way from what Babbage wrote. Mark I had one set of storage, which was a bunch of switches. It was a big panel. Now the Mark I word consisted of 24 digits, a sign and 23 decimal digits. So across the panel were 24 switches, and you could turn them to the different numeric positions and put constants into a problem by setting them up in the switches. Our switches on Mark I really did very well. The only time we got into trouble with those switches was on Mark II. Mark II also had a big panel of those switches, and you could set numbers in them for the constants for the problem. The crew went out to lunch one day, and they were computing the trajectories of some shells or something. And when they came back, they found out to their complete horror that all of the shells were turning around and hitting them. And they practically tore the machine apart trying to find out what had happened. They finally checked up on what had happened during lunch hour. And it turned out that the Admiral had come over to show some people his beautiful new computer. And he'd said, "This is where we put the constants in." And he had changed the constants enough to reverse the firing pattern. After that, the constants were all locked. There was a lock put on the glass door, and they were locked up so that nobody could change them. Mark I had 72 storage locations, each consisting of 24 positions, would hold a sign and 23 decimal digits. Each of those storage positions was also an adder. So when you read out of one counter into another one, it added to the contents of that counter. In other words, essentially you had 72 adders in the computer. All of these were tied together by the main bus. The instruction was essentially a single address instruction, except I've never seen anybody call it that. Because we wrote in 3 columns. One column was the out column, one was the in column, and the C column was the action column. For instance, a multiply instruction would be 432 out of counter 432, 761 into the multiplier, and 7 to go on to the next thing or whatever. And the in column was essentially the operation to be performed. So it was really a single address code, except that you named the quantity first, then the operation. And the third column was the one that, for instance, would tell a print counter to go ahead and print, or the punch card counter to hurry up and punch that card, and so on. Various action codes were in the third column, along with the automatic, which moved it to the next step, which was the 7. So with the 72 of those storage registers, each one of which was an adder. The next important unit was probably the multiply-divide unit. It was a decimal multiply-divide. The multiplicand went in first, and then in the registers in the multiply divide unit were built up the 9 multiples of that quantity. You build up 2 times, and then you double it, you get 4 times, and so on. There are nice ways for building up the 9 multiples and storing them, being able to read them off. The multiplier came in, and it called down the multiples of the multiplicand one after another, and shifted each time and multiplied just exactly the way we do when we try to do long distance multiplication. The divide unit was the same. You build up the multiples of the divisor and then subtracted them till the sign changed, and then got another one, and so on and so forth, and performed division very much the way we perform division, except you subtracted one thing after another. One nice thing about the multiply divide unit was that once you had transferred the multiplicand into the unit, there were 2 cycles during which the multiply divide unit did not use the main bus. It used only the multiply divide unit. So you could sneak some extra additions in on top of that and do things in parallel, and then read in the multiplier. And then you could sneak some additions in parallel with the rest of the multiplication process. There was a catch in that, though. If there was a 0 in the multiplier, it just shifted across, and it didn't occupy a whole cycle time. So unless you were pretty darn sure how many digits you had in your multiplier at all times, and how many there were going to be, why, you could get into trouble by not allowing enough cycles for the multiplier. And if there was one thing that drove Commander Aiken nearly crazy, it was not hearing the sequence mechanism step. Because the sequence mechanism stepped 3 times a second. The sequence was punched into a paper tape. It was the standard cardstock, 24 holes across, 888 for the in code, the out code, the in code, and the operation code. And the sequence mechanism read those rows of 24 holes sequentially. Now, if you didn't keep everything in that machine busy, it would hesitate while it was building up multiples of the multiplicand or something, and it wouldn't step till it got to the next move ahead signal. And if there's anything he hated, it was to hear that machine be quiet. So sometimes you did some very interesting faking on top of the multiply in order to make sure the sequence mechanism was still operating every single second, 3 times every second. It was decimal, and in order to take care of subtraction, it was complements of 9, so that there were 2 zeros in the machine, +0 and -0. +0 was all zeros, -0 was all 9s. We had one mathematician on the staff who insisted, to the day and the end of the war, there was no such thing as plus and minus 0. It was just 0. Well, the check register tested on the sign of the quantity, and every so often his programs would stop, and Aiken would look at me and say, "Go fix that." And the first thing I always looked at was to see if he'd tested on 0 and gotten the wrong one. He usually had. It was hard. To me, it made perfectly good sense. Because if you come down in the positive quadrant, you're coming down with positive numbers that get smaller and smaller as you approach 0. Eventually they drip off the end of the machine and you get all zeros. If you're coming up in a negative quadrant, the numbers get smaller and smaller and fall off the end of the machine and eventually come up with all 9s, and that's a negative 0. And so both positive 0 and negative 0 made perfectly good sense to me. But I assure you that they upset a very large number of mathematicians and provided a great deal of difficulty with the check counter when people tried to compare for the sign. Mark I also had some other built-in units besides multiply divide. It had a sign unit, log to the base 10 and 10 to the x, logarithm and exponential. They were built out of relays. They had the stored constants. They expanded those normal series functions. There's only one thing wrong with them. They took too long. Because no matter what you did to that sign unit, it persisted in computing the sign to 23 decimal digits. Well, practically nobody ever wanted 23 decimal digits. It also persisted in doing the entire reduction of the sign when you might know perfectly well that your sign was positive in less than pi over 4. So a very interesting thing started developing, which led to other things later. We began to have pieces of coding in our notebooks. For instance, Dick had a nice little sign program for angles less than pi over 4, positive angles. And when I needed it for another program, I'd borrow it from his notebook and copy it into another program. We didn't realize it, but we developed subroutines. And the whole future of beginning to get the compilers and the various high-level languages came from those things in the notebooks. And both Bob and Dick had notebooks full of those pieces of code. And believe me, I borrowed them very frequently. I also learned another lesson at that time, which later forced me into the development of the compilers, and that was that programmers can't copy things. And that when you integrate a piece of code into another program, you frequently have to add to all the addresses. And programmers can't add either. Those units eventually were not used because we had the pieces of code which substituted for them. Ultimately, they were torn out of the machine because they were not used, because they were stubborn enough to always deliver 23 decimal digits. The timing, particularly on some of those units, is really colossal. I'll remind you that at the time these were not so bad. Addition took 3 seconds, 3/10 of a second. Subtraction took 3/10 of a second. Multiplication took 6 seconds. Division took 11.4 seconds. Log to the base 10 of x took 72.8 seconds. 10 to the x took 61.2 seconds. Sin x took 60 seconds. So she was not what we would call today a terribly fast machine. However, a study was made competing with the computer against a human being with a calculating machine. And it turned out the ratio seemed to be about 100 to 1. So that it looked as if in the period of a week, a computer in a period of about 6 hours could do what a calculating machine could do in a week. And this looked to be very favorable in trying to meet the computational needs of the system. In addition to those units, there were 3 other units which were unique to Mark I, and those were the interpolator units. I believe that they were basically Howard Aiken's own concept. They read paper tape. The tape contained numbers across the tape, 24 positions. And what it would do is you send an argument to the interpolator. The interpolator would then step through the tape until it found that argument. When it did, it would read the corresponding interpolation coefficients and then apply the usual interpolation formula to give you the value you'd requested. And there were 3 of those, which provided for adding in other functions besides the sine and the log and the exponential. I only knew one person ever who was able to write a complete program in ink and have it run the first time, and that was Dick Block. I think he drove all of us nearly crazy because he could do that. He also had another rather interesting quality. She was a relay and step counter machine. Therefore, it was not too difficult to change the circuits. Every once in a while, Dick would get an idea of a new circuit that would make his problem run faster. And he would get together with one of the operators during the night, and they'd fix the circuit. The next morning when I tried to put my programs on, they wouldn't run. So it's much safer to have a routine, a machine, which the programmers cannot alter. It's not good to turn them loose and let them change circuits every night. The main sequence mechanism was the same, looked the same as the interpolators. It was that same cardstock tape, 24 holes across, 8 for out, 8 for in, and another 8 for the operation to be performed. Incidentally, changing a sign was rather interesting. What you did was read out of one counter into the other and put a 3-2 over here, and that changed the sign. That was considered an operation rather than a transfer of data. I don't know whether I've made it clear, but the data and the sequencing were totally independent. Throughout the development of Mark I and Mark II and Mark III, Howard Aiken always insisted that the data and the program must be independent and stored independently. We lost that for a while when people came along and said, oh, we want to store the program in the same memory as the numbers so that we can alter the program, and that may put more bugs in than anything else ever did. Only in the last couple of years have we come back to recognize that we must keep the data and the program independent and in separate memories, one acting on the other. One other thing I can remember particularly about Howard Aiken, people would look at all the length of Mark I. In fact, I had a favorite story. People would ask me what the long drive shaft did. That turned, of course, all the cams and counters. And I told them very carefully, we just dropped a card in this end and that traveled down the shaft and then went up into one of the registers. They believed me. Of course, anybody believed anything about Mark I at that point in time. Howard Aiken always insisted that someday he was going to have a computer which would fit in a shoebox. I don't know how he knew that, but he certainly did, and he predicted it all the way along the line. He was a tough taskmaster. I was sitting at my desk one day, and he came up beside me, and I got on my feet real fast, and he said, you're going to write a book. I said, I can't write a book. He said, you're in the Navy now. And so I wrote a book. I have it here with me so that I can manage to answer any questions. This is the Mark I manual, the entire Bible of Mark I. It contains every circuit, samples of all kind of programming, coding. Has an excellent bibliography in it on computation. Has timing charts for all the operations and the various circuits. All the circuit diagrams are in here. You could take this and build Mark I over again if somebody felt like it. It might be fun to build one out of chips. The major problems came one after another. We continued to be under very heavy pressure from Washington and other places to hurry up and finish each problem. I can remember one I got. It was to compute the power of a dipole which was being towed behind a ship to sweep for mines. And they wanted the value of the effect of the dipole every foot for 20 feet in every direction. Well, it was more than that, 200 feet, I guess. Anyhow, I totaled out how much paper it was going to be and found it would be the same size as a cord of wood. And I said, this will not be very useful. I also found that the attenuation went up in a sharp loop and then trailed out this way. And beyond a certain point, it didn't even change value in the 8th or 9th decimal place. So I said, will you settle for going out where the decimal places don't change anymore? And it turned out to be one small book about this big. It showed us the strength of the dipole towed behind a ship. People had little concept of the effects of computation. Once you had a machine, they wanted everything. They didn't stop to think what was going to come out as the results and how many results there would be if they insisted on putting their intervals too small and so on. There were many other classes of problems that were coming up. Solutions of sets of ordinary differential equations, solutions of partial differential equations, iota matrices. Many of these things were first run on Mark I. It took an awful lot of time, I'll admit, but the answers came out, which was, of course, the critical thing at that time. It was very interesting to go back here and look at what is required in running the computer. It mentions the storage, the switches for the constants, the tape racks, because of course we had a long problem. It went up and down on the tape racks this way. And you had to be very careful how you mounted it, because there's a certain pull on those, and if you didn't get it mounted right, it didn't move, which has made life a little difficult occasionally. The multiply divide units, the various functional counters, the interpolators. It had 2 typewriters for printing out the results, 2 electric typewriters. It also had 2 card feeds for feeding numbers in, and it had a card punch for putting out numbers. We regarded those as slightly slow, but not very. One interesting thing about the card feed, the card punch and the tape punch, was that they were buffered, in the sense that you read a quantity up into the punch register, and then you gave it a signal to start punching. And it would go on from there punching while the computer went on operating. You just had to remember not to try to read into that register unless you'd gotten that punched. There's also a description in here of how a program must be delivered. It's something we could well give to most of our programmers today, because it suggests that when you write a program and present it to the computer, there are several parts that must be provided. The first, of course, is the coding, which will control the sequence mechanism. The second is the plugging, and you must describe the plugging for whatever decimal point you've chosen to run by, whether between 12 and 13 or 9 and 10 or what, all the plugging for the multiply divide unit and other such units. And then you must provide operating instructions for the operator. That far back, we were still trying to get programmers to annotate their coding and to provide operating instructions for the poor operator who was going to try to cope with this thing in the middle of the night when you weren't there. And so it does specify that there should be operating instructions as well as the coding for the problem, the setting of the constants, and the other operations to be performed. And many times there was a preliminary tape to be read to clear part of the registers before you read things into them. So the specifications for presenting a program to the computer are probably as old as the first computer. And you know, the darn thing is we're still trying to persuade those programmers to write those operating instructions and to write those comments on their code so somebody else can understand what it's all supposed to be about. It was good discipline and did produce amazing problems were run and tremendous jobs were done on old Mark I. How can I tell you what it was like to walk in and look at all about 51 feet of her and be told it was a computing engine? Of course, one thing that influenced me was that I'd always loved a good gadget. When I was about 7 years old, we had a home up near Wolfboro, and each bedroom had a clock. Those round clocks with a bell on top and 2 feet that shake apart when they go off. And when we were going on a summer hike or a trip or something, Mother would go around the night before and set the clocks for us, her children, and all the cousins that were visiting. She went around one night and found all the clocks apart. What had happened was I'd taken the first one apart and couldn't get it together. So I'd opened the next one to see how to put that one together, and then I'd opened the next one. After that, I was limited to one clock. But I'd always loved a good gadget. And I'm afraid that in my heart, when I first saw Mark I, my first thought was, gee, that's the prettiest gadget I ever saw. Which probably would not have pleased Howard Aiken had he heard it. She gave us a great many things. I mentioned the fact of documentation. complete documentation of a problem. That was developed on Mark I. I mentioned those pieces of coding that we kept copying out of Dick and Bob's notebooks. The next thing that helped us in that direction was the book by Wheeler Wilson Gill, who actually built a set of subroutines before the computer was finished to compute those various functions and things. As time went on, Mark II was finished, and Mark III came along. And there was built for Mark III something which was never built for any other machine, a coding machine. It had a tremendous array of keys stored in relays with the various subroutines. And when you wanted to sign, you hit the sign key, and cluck, 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 it ended it in the tape. Plus, it added it, cosine, cluck, 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 and it punched it in the tape. All these subroutines were stored in relays, and with this magnificent keyboard, you could punch these, and you punched in, essentially, the program you wanted to run. Probably the only coding machine, as far as I know, that was ever built. But what it did was automatically fit together the subroutines that we'd been using. It was not till 1952, much, much later, when I had gotten totally disgusted with all of our programmers because they couldn't copy things accurately. In fact, they'd take a 4 and turn it into a delta. A B always turned out to be a 13. It was terrible. They couldn't copy accurately, and they couldn't add to those various steps, because sometimes they had to add 7s and 9s. And there sat a machine whose whole main job was to do addition and to copy things accurately. And that was what led me to write the first compiler back in 1952. But it stemmed originally from those pieces of code that floated around in our notebooks, that there should be a better way of copying those and integrating them into a new problem. We should not have to do that stuff over again. And that was fully confirmed by the Wheeler Wilson Gill book, which came from England and gave us a step forward in that way of thinking that finally turned out to give us, ultimately, the languages which we have today. So many of the things that we don't recognize where they came from or how they got started originated in those very, very early days, the very beginning of trying to use computers. Aiken didn't consider a program complete until you submitted to the operator the coding, the settings for the switches, the plug settings, and the coding had to be annotated to tell you what it was doing, and operating instructions for the operator. And it didn't go on the computer, supposedly, until that was complete. Though, of course, Dick frequently got away with running things without having the operating system's instructions complete. But many of the things that we think of today, common, ordinary, or have forgotten where they came from, arose in the development of the first programs that were written for Mark I. Mark II, of course, was even more fascinating. It was built while we were running Mark I. It employed a concept which has not been employed since. Mark II could be run either as one single computer, or it could be run as two computers independent of each other, who can converse to each other across the transfer records, or as a master computer and a slave computer. It's the first true multiple computer I ever saw built, and it contains some things which have not yet been used, such as the transfer registers have not yet appeared in our new computers, and I trust that someday somebody will recreate them. There's much that we could learn about going back and looking at these early things. The concept of the independence of numbers and of data and program. Of course, the concept of sequential program is now so accepted we don't think of a computer going any other way, though we're beginning to put things in ROM instead of in plug boards. Whether that's the same thing or not, I'm not quite sure. There are many things we could discover by going back and looking at some of the concepts which are lost along the way, because those early machines were so slow. I know they were built out of relays and step counter. They were electromechanical. They're not very interesting. Yet I'm willing to bet that almost any one of you could pick up this big volume and look through it and be somewhat fascinated by the things that Mark I could do and the things she did do, and the really amazing ingenuity of the way she was strung together and the way she operated. I think we can all be quite proud of the crew that operated that. Aiken for his ideas and concepts. He went to IBM. Mr. Watson supported it. Some parts of the computer had been designed by some of the IBM engineers. They worked with us for quite a while. It was a tremendous accomplishment to get that thing built and running. It was also, I think, an accomplishment for the crew that ran it and kept it going and maintained it morning, noon, and night for those war years. And the pressure, believe me, was heavy. The stress was very great to get everything done yesterday. And believe me, Howard Aiken helped to apply it. He was very good at that. So I'm very proud of the fact that the first large-scale digital computer in the United States was a Navy computer, just as I'm proud that I once again wear the uniform of the United States Navy. Over these years, I've had a lot to do with computers. I've driven a large number of people at least partially nuts. After all, insisting on talking to computers in plain English was a totally ridiculous idea, and you couldn't do that, except it worked. And I've been grateful for all the help I've been given and for all the things that have happened to me. I've also received a large part of the honors that are given anyone in the computer industry. I've thanked him very much. But then I've also told him I'd like to repeat to you. I've already received the highest award I'll ever receive, no matter how long I live, no matter how many more different jobs I may have. And that has been the privilege and the responsibility of serving very proudly in the United States Navy right alongside Mark I.